So, couple quick announcements. So first off, midterm average, again, all the individual ones are done. I'm going to be releasing those a little bit later today. Midterm average is 65%. The group midterm, much higher. And again, if you've done the group one, that will adjust. It'll get all those posted up on Canvas, both your individual and your group mark, later today. Today is our last in-person lecture. Friday's off, Monday is off. Next week, we're up into our final part. There will be no classes next week. In the final week, before coming up to the actual final, we're going to get some more time available to do either office hours or review sessions based on availability. These may be Zoom sort of dial-in components, but we will go through that. Canvas Quiz 6, this is the last sort of one of your 6. Remember, the way this works is we keep your best 5. Canvas Quiz 6 here, this is the last of our sort of formal 6 ones you can go through. It is due tomorrow at 5 p.m., not Friday, and that's really just to help accommodate for both opening up Canvas Quiz 7. Quiz 7 is not for marks, it is for practice only. It just continues the same kind of quiz questions for things like the Sigmatropic rearrangements, the Diels-Alder reactions. It's practice for you guys to work through those parts. So do it. It's a good thing to practice on, but it's there for your benefit. Last TA tutorial is going to be Tuesday, April 7th. So that's going to be next week at that part, same time, same place. A couple other things important. Final exam information. Remember, it's going to be here. We're in the SRCA, that massive room. It's going to be noon to 2:30. Closed book exam, 2.5 hours. Cumulative, however, it's mainly focused. Think about it as a breakdown of about 40% the later content, 40 to 45, and then the rest of it distributed amongst the others. Again, it's a hard thing to make a discrete cut because all the material we're talking about, arrow pushing, acid base, whatever, is consistent through the entire course. So that does cover all concepts for different points. I will be posting up sample finals up onto Canvas, and just like midterm 1 and 2, bring your student ID. This one is really, really important. You have to have your student ID with you for writing your final. We will be taking attendance in that part too. Last class, we went through inverse electron demand Diels-Alder reactions, Sigmatropic rearrangements, Cope rearrangements, and Claisen rearrangements. So this is the final part of what we were calling this kind of other class of reactions based on pericyclic reactions. These are concerted reactions where we're usually involving multiple arrows at the same time, moving sigma and double bond. Before we get to that, though, thank you guys for voting at the last minute. What I would like to announce first, just so you guys can get good and wired on sugar before the final thing, is our group names. So I don't think I had a slide on it. So of the ones that you posted up, wow, that one just popped up. Somebody's voting. I'm going to call the dial-in vote rigging. Okay, number 3. Anyone want to do drum roll? The disasteomers. Are you guys here? Okay. Low toss. Number 2, you guys pulled ahead at the last minute, miso soup. Good job. And an overwhelming, shattering number 1, does anybody guess? The barely functional groups. That was epic. I love that. I may have voted multiple times. Okay. So, review question from last time. You guys have been looking at sigmatropic rearrangements. This is a 3-dimensional representation of a sigmatropic rearrangement. Based on this, so note the things, like you've got to find your components. What would you class this as? So the numbering scheme and the naming. If you go back to what we talked about last time, what is this? 6-2, 1-3, blah, blah, blah. How would you name this in terms of your numbering point? Second, what does this look like? Cope, Claisen, Diels-Alder, blah, blah, blah. What does this look like? Okay. So first, name. What does this look like? What would you name this? Somebody give me an answer. You can kind of see it here. This looks kind of like a C. This is a cope. It's an alkene with a sigma bonding system, 2 alkenes on both ends. This is your cope, right? So from that, how would you name this? 1, 3, 6, 1, 12, 5. What is this for numbering? 3, 3, yeah. The way you can tell it is, look at your transition state. You have 3 atoms here. You have 3 atoms here. This is best designated as a 3-3 sigmatropic rearrangement. Why do you think this happens? You have to make if you had to make an argument for why this forms the product, what's the thing that's helping you out here? Why is the product more stable than your starting materials? Yeah. Exactly. This is something where you've got, not only are you breaking a bicyclic system, right? We're going from this tortured molecule that's sort of set up as that point. This is just that same geometry. When you lay it flat, when you lay it flat, it looks like this, right? So you're actually breaking a relatively strained system. But also, right there, after tautomerism, it locks in that component. It's able to go through a retroreaction because the ketoform is going to be more stable. This is what we call an oxycope type rearrangement. So good. All right. So what we're going to talk about today is kind of the soup to nuts. As of now, we have covered all content for everything in the class. So you guys are officially, again, if we did this point from some component, you know all the spells I can teach you in this class. What we're going to talk through today is applications. This is how we use those components to do actually more significant synthesis, and more importantly, using it for what we call biologically relevant molecules, polypeptides. Especially this year, does anybody ever know, if I told you what is a really important peptide that's kind of changing global health right now, does anybody have an idea of what that molecule might be? What's that? Oh, Ozempic, that's right. No, seriously. If anybody's looked at the structure, Ozempic is interesting. Like things like molecules like insulin, these are peptides generated by the body to act as both hormones and signaling transduction components. These are really interesting molecules that are really important for metabolic regulation. Ozempic, GLP-1 inhibitors, is a brand new class of drugs that we've only recently been able to look into, and depending on what you read about them, they're everything from, the promise that they actually have as a category is actually pretty impressive. But if you look at the structure, it's a 30, 50 amino acid. It's literally just a synthetic polypeptide, so no different than a single piece of protein. The difficulty with it is you got to make it. Synthesis of these molecules, they're not smaller molecules anymore. They're not macromolecules made by biology. They're in the middle where you need to make these relatively long, very well programmed polymers and actually decorate them to actually become something that's actually a druggable material. In order to do this, we actually have to basically emulate biology. What we have to do is, if you look at the class of molecules for peptides, what they really are is repeating structures of subunits. Remember, amino acids get coupled together to make peptide bonds. So your primary structure of your enzyme is the sequence of amino acids. The secondary structure is local turns. Ternary structure is the entire folding. We're not talking about ternary. It's mainly that primary structure which influences secondary structure, and that's where a lot of the biological activity comes in. So the amino acids, we've talked about this part, those are your building blocks, and you can use the native building blocks like the amino acids we have from our natural sources. That means isolation and using those 2 points. The fun thing is, as synthetic chemists, you guys can make up amino acids. So if you had to synthesize this racemically, going way back, this is a deep cut now. How do you make this? What's the reaction? Strecker, right? You can go use cyanide to your heart's content, and you can make your own amino acids. The nice thing about this is Strecker allows us to install really this part of the group. Yes, there's a chiral center. There are ways when you get to third year that you can control the chirality, or even better, make the racemic material and then split the chirality. That's easy. What's really cool about the Strecker reaction is not only can you say, I will make different chirality there, but I can also change the payload. I can change what's on that functional handle, because what is the molecule? Going back, yes, there's a Strecker reaction. What do you make a Strecker reaction from? What I mean is, this carbon fragment here comes from what kind of molecule? What functional group do I need? Aldehydes. And you got plenty of ways to make aldehydes. So any R aldehyde allows me to put that R group in as my payload for my amino acid. Great reaction. You've got lots of variability. You can go nuts in terms of your ability. So that's problem one. You got to make your amino acid. But once you've done that, now you have the building blocks to make up a polypeptide. So like I said, Ozempic, anything like this, it's just a sequence of amide bonds where what you're doing is taking a very structured polymer. That's an amino acid. Then you have your next amino acid. Then you have your next amino acid, on and on. Each of them is just segregated by these one-by-one sequencing. Amide bonds link them all together. So think back. We talked about a whole chapter about this. How do you make amide bonds? If you guys had to go to the lab right now, we talked about those energies. Remember, nucleophilic acyl substitution reactions. We have those 4 different levels of reactivity. What's the most electrophilic guy up in the top corner of that slide? Up over here, that's a what? Acid chlorides. Down from that is what? Anhydrides, right? So you could choose acid chlorides or anhydrides. Those are very electrophilic molecules. That's your electrophile. And then you just have to couple in a nucleophile, right? And the nice thing about that is, okay, we've got a carboxylic acid here, nucleophile there. What can you not do? You can never take an amino acid and a carboxylic acid and put them together, right? If I took just that molecule, my amino acid, and just boiled the crap out of it, what happens? Acid base, nothing else. You're not going to make amide bonds by having a carboxylic acid here and a nitrogen there. The acid-base reaction will persist. One is not nucleophilic. Now it's not electrophilic. Nothing happens. You have to activate it first. So we can do this. I could take an amino acid. I can treat it with thionyl chloride or POCl3, and I can convert the carboxylic acid point to my acid chloride. Those are all the reactions that we've done before where no problems there. And again, I could do this separately. Let's say I have 2 different molecules. I take this one where that R1 payload makes that amino acid, that acid chloride. Take this molecule, that payload, that one. If my goal was to programmatically add these guys together, what happens if I take the acid chloride in the top, the acid chloride in the bottom, mix them together? Is there a problem? Am I only going to get one product? Heck no. The problem you have here is you've got, up top, a really good electrophile and a pretty good nucleophile. And down here, a really good electrophile and a pretty good nucleophile. If I put them together, I get a mess. I get every combination that's possible. So I get light blue coupling with light blue to make the homodimer down here, right? This guy can couple with itself to make this compound. This one couples with itself to make this compound. I get that acting as a nucleophile, and this is my electrophile, giving you this one, and the opposite as well. All 4 possible products that are here. This is just, this is just stoichiometry, where since you have a molecule that's both nucleophilic and electrophilic, each will work, and you'll probably get a statistical mixture of all 4. Yes? It depends what the R group is. Good question. Does the R group react with SOCl2? If it was a benzyl group, if it's just alkyl, like isopropyl from something like a valine or something like that, no, it's fine. If that R group contained an alcohol, a carboxylic acid, something else that's other nucleophilic, then yes, that will also further react, right? Anything like alcohols, any other reaction you can do with SOCl2, if that function group is buried in your R group, then yeah, it's a problem. So it's possible. There's one more complication. Again, it's not a really key thing here, but as it also turns out, look at this combination. We're assuming that that stereocenter is preserved, right? If it came in as R, it's going out as R. All we're saying is nucleophilic coupling is possible between these two. Turns out that, what do you think happens to the relative pKa of this proton after you've made it electrophilic, after you've made that center? Does it go up? Is it more acidic, that hydrogen at that alpha center, or less acidic by putting an acid chloride next to it? By putting a powerful electron withdrawing group here, what do you think I did to that acidity of that proton? Is it more acidic or less acidic? It's actually way more acidic, right? Because any anion that I form there is going to be stabilized by electron-electron group. So what happens from this too is if you go and do this strategy, and this is actually something I learned very painfully in my PhD, not only do you get these 4 products, you get every isomer flipping as well. You actually reset that stereocenter. So you get R and S of each one of these ones, which means you just made a boatload of garbage, right? Because not only can you not control your stereocenter, you also have every combination. Sorry, up at the back I saw a question. Yeah? You mean this? That's the next problem. Even if you managed to succeed and you made all 4 and you're like, you know what, I'm really good at chromatography. I will make every possible product and I will isolate only the one that I want, but now I'm going to make it longer. Now I want to elongate this because a dimer, 2 amino acids, is not what we're looking for. We're looking for these longer chains. The problem you run into now is if you took a molecule that has a nucleophile and this, and if I tried to run another reaction, the next elongation, it will actually more rapidly dimerize on itself rather than adding anything else. You end up with these cyclic products here. Basically, this is not how you do amino acid synthesis. Yes? Amides to nitrile? Yeah, it's possible, right? If you took these, well, not so much. The amide in the backbone isn't going to go up to a nitrile as easily, right? But basically, the point is, this is not going to help you. This is not your way forward. You cannot do this. So the solution is what we've discussed multiple times. If you have functional groups where the relative cross-reactivity is screwing you over, you need to protect them or temporarily mask certain functional groups. The amino acid is our building block. That's true. The problem we have here is an amino acid is both a nucleophile and an electrophile, so we need to temporarily make one thing not nucleophilic, only an electrophile, and something else not electrophilic, only a nucleophile. So we're going to use our protecting group chemistry, and that means if you look at the amino acid, we have 2 big problems. We have a carboxylic acid that we need to differentially protect. We have to turn it off and say, no, it's not an electrophile anymore. And we have a nucleophile, the nitrogen. And I have to protect the nitrogen and say, you're not going to act as a nucleophile now. So we have to come up with a series of protecting groups that, number 1, will selectively protect the nitrogen or selectively protect the carboxylic acid. And 2, we need the ability to deprotect it surgically. If I have an elongated polymer, I need to be able to deprotect just the nitrogen and not touch the carboxylic acid, and vice versa, which means we actually have a whole set of different ones. There are 5 protecting groups we're going to talk through. So let's start on nitrogen. If you have a nitrogen group, the way that you cap it is turn it into something like an amide. But remember, if I had to hydrolyze amides, amide hydrolysis is actually pretty tough. Not just that, if I tried to cap my amide and then I try to selectively cut my amide, well, my backbone is made of amides. So taking your nitrogen and temporarily trying to cap it as an amide is not a good idea. We cap it as something called a carbamate. A carbamate is where if you take a molecule like this acid chloride looking guy where we've got an oxygen on the other side, if I use a nitrogen to attack this group, what I make is something that is R, nitrogen, carbonyl, oxygen, R prime. This is what we call a carbamate, a nitrogen carbonyl oxygen sort of fragment. So what I'm doing is I can protect a primary amine by using this guy. This is called a chloroformate, doesn't matter, but think of it as it's just an acid chloride where there's an oxygen on the other side of the carbonyl. And the way we differentiate them is we have these 3. These nomenclature, Bock refers to T-butyl oxy. It's this tertiary butyl group here. Now that's the first. The second one is we call CBZ or Z. That's benzyl oxy. The Z for benzyl oxy right there. And then there's what we call FMOC. It's this fluorine blah, 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 whatever. It's this. Looks like a pollen grain. You see the difference between each 3 is just that R group. FMOC, CBZ, Bock. Those are your 3. And the thing that matters between them is, again, how you put them on each case is identical. They start as kind of this acid chloride kind of surrogate. You react it under the same conditions you use in acid chloride, your amine plus your base. And that's how you install it, where what we're doing is we're changing the nature of that OR group. And the reason why is each of them is sensitive to a different deprotection conditions. So Bach, interesting thing about Bach can be deprotected by acid. It is acid sensitive. So if we install a Bach group, I can selectively clip a Bach group by treating it with a bit of acid. That's why we use it. CBZ, we install it the same way. It's under basic conditions, but we selectively deprotect it using hydrogen and palladium. Remember back, lecture 29, we talked about I can remove an O-benzyl group by hydrogenation. So I can hydrogenate the Z group. And then the last one, FMOC. FMOC is base sensitive. More importantly, it is nucleophilic base sensitive. Pyridine, or piperidine. Piperidine is this. It's a 6-membered ring with an NH. That is a really, really, really good way of unstitching FMOC. Turns out that this proton right here, if I deprotonate that center, what do I make? I make an anion if I remove that green proton I just put on there, I make an anion which is now resonance stabilized. So I have 3 different OR groups, one that is acid sensitive, Bach, one that is H2 sensitive, Z, and one that is base sensitive. This allows me to say, depending on which one of these groups I have, I can now match this with other functional groups or other protecting groups that are going to be orthogonal. In other words, I don't necessarily want to use Bach if there's other protecting groups in the molecule which are acid sensitive. Think back all the way through the course. Give me one other protecting group, maybe in their first 2 lectures, that is acid sensitive. What's another protecting group you will cut off from a carbonyl type compound with acid? Acetals, ketals, right? So I would not want to use Bach if I'm using an acetal somewhere else in the molecule. In case there, I would use the acid to cut off my acetal, and I might use FMOC on my nitrogen because it allows me to selectively deprotect the nitrogen with base, and then when I want to, come back later with acid and cut off my acid-sensitive group. This is how you're using them, is you're picking which group would deprotect it. It's 4D chess time. So here is how many amino acids have we coupled together here? If you look at this guy, how many amino acids are represented here? 5 amino acids. Remember, the amino acid, what you do is you look for your core backbone of your amino acid. That's your repeating chain. Stuff branching off of it is your R group. So if this is your core amino acid, how many amino acid subunits do we have? It's basically count the amide bonds, only amides. There are how many? There are 3. There is this guy here, is 1 amino acid. That's number 2. This is number 3. These other chunks are your R groups in this case. So it's 3 amino acids, a tripeptide, your backbone. You've got a bunch of protecting groups decorating this guy over here. Go through each of these for a second. If you took that molecule and you hit it with heat and piperidine, which nitrogen gets exposed? So this is where I look back at the last slide. What we're really asking is, given that molecule and the protecting groups that are present in this one, which one is sensitive to cleavage by piperidine? Okay, as a one creepy voice, A, B, C, D, or E. Which nitrogen do you open up with piperidine? It is, that's right. This is your FMOC group. Base with FMOC will open up the nitrogen, only that nitrogen. That is your base-sensitive one. Look at the rest of the molecule. Yes, base will deprotonate this. Doesn't do anything. You need more base. You're not going to cut all the other ones. Remember, these core ones in the backbone, those nitrogens, or at least the main 2 nitrogens, B and C, those are just normal amide bonds. With strong acid and heat and time, you might hydrolyze those, but those are probably your more stable ones. You focus on the carbamates, which are your others. Okay, what about H2 palladium? Again, take a second. If I took just that starting material, hydrogen palladium, which nitrogen opens up? One together, it is D, right? This guy here, that's your Z group, right? This is your CBZ. Sorry, you're going to get it on the recording, but it turns out for April 1st, the app that I use creates a duck that is walking all over my screen, so it's going to be very distracting for me, but you guys see nothing. Just warning you, if you watch this later, or if you're watching this for the first time because you're not here in class, yeah, there's a duck. I'm not crazy. I did not come to class drunk. Yes, you will open up D. Last one. If you use this guy, what's that thing called? CF3, blah, blah, blah. That's called TFA. That's a strong acid. TFA opens which one? A, B, C, D, or E? It opens up? A. Yeah, A. So only, those are your 3 carbamates. These are your 3 ways of selectively exposing the nitrogen you want for other follow chemistry. So what you're doing now is you've got this way of multidimensional chess. You can choose a molecule that looks like this, and depending on which conditions you want, you can programmatically open a nucleophile that helps you out. Okay, that's the nitrogen. You have 3 different nitrogen protecting groups that you have to remember: BOC, CBZ, FMOC, and those correspond to acid sensitive, H2 sensitive, base sensitive. On the carboxylic acid, what's a way of turning a carboxylic acid not into a carboxylic acid? If I don't want to turn a carboxylic acid into an acid chloride or something that's electrophilic, I can convert it to an ester, right? What are your conditions? How do you make esters? You have a whole bunch. We talked through all these different ones. Esters, you can make them by Fischer esterification, so acid catalyst. Yeah, what else? What's another way to put in an ester? Diazomethane, if you're insane. Yes, there's one more group that actually really helps out. Your tertiary butyl group, right? Your T-butyl group can be installed under acidic conditions. That's where you're adding to like isobutylene. And the nice thing is, if you've got those 2 different ones, normal esters are base labile. That's saponification, right? If this OR is equal to like O-methyl, O-ethyl, those are selectively cleaved by saponification. I can treat it with strong base, that will cut my ester. Strong base won't touch your amides. Remember, you need acidic conditions mainly to cut off your amide bonds. So base is great for cutting this one off over here. However, if you had a base label carboxylic acid, which nitrogen should I not use? Which nitrogen protection should I not use? If I had a base labile carboxylic acid, which nitrogen is a bad choice? Because I'll hit the base label acid or base label carboxylic acid, but I'll also hit my base label nitrogen, which is base label FMOC. So again, unless you really want to open up both the nitrogen and the carboxylic acid at the same time, if you've chosen FMOC as your nitrogen protection, do not use O-methyl, O-ethyl, because they will both cleave under basic conditions. However, if I've chosen FMOC for my nitrogen, base labile, then I can choose T-butyl as your selective acid deprotection. Bonus question, everybody. How do you cut off a T-butyl group? Better not be with OH. Yeah, I know, that's a hot take. I'm sorry, guys. You can't cut a T-butyl group off using hydroxide because it's too bulky. Saponification is a bad choice, especially if there's other esters in the molecule, like in the penicillin point. Acid is beautiful for cutting off a T-butyl because there's a selective deprotonation that you can do where this is a T-butyl group. It is acid labile. So now you've got a way of saying I can choose base label nitrogen, acid label carboxylic acid. That would be FMOC T-butyl. Or you can invert it. I can have a base label carboxylic acid, O-ethyl, and I can have an acid label nitrogen. So that would be BOC. Or you can say none of the above. Nitrogen could use your CBZ. That is hydrogen labile, which doesn't touch your carboxylic acid. So this is why you have these 3 different dimensions. Man, that duck is really bugging me. Okay, so now that we've got the way of doing programmatic capping, how you actually build up amino acids is by choosing the right protecting group and using the same kind of strategy where we do a coupling reaction of the properly protected groups. We then deprotect whatever site we want, and then we carry out the next coupling. So let's say we start with the molecule here. We've got our purple R and our green R. That is our dipeptide. And notice what we've done is I chose under here, I've got this protecting group on my nitrogen. I've got this protecting group on my carboxylic acid. What I've done here is I've taken my dimer, and this is strictly my nucleophile, and the other is strictly going to be my electrophile. I've chosen those two as a pattern. Now again, we're not going to show you the chemistry yet, but the strategy here is go in with an exposed carboxylic acid, that's where I'm going to do my electrophilic activation, and I go in with my exposed nucleophile on the other side that allows me to make only this bond, and it will always give you this particular reading sense. The N terminal of your peptide is over here, your C terminal is over there, and it only gives you this purple-green compound. You don't ever have green-purple, you only have purple-green because you've chosen which one is going to be electrophile and nucleophile. You've identified their roles just by protecting them accordingly. Now, once you've made this dimer, you choose to deprotect it. You can choose either. There are both strategies you can use. You can either do what's called a C deprotection, like you see here. We're cutting off the red protecting group that exposes this new electrophile. Or you can do the other side, the N deprotection, in which case you expose a new nucleophile. Either of them are available. It depends on which protecting groups you have and how you're building up your amino acid. But in this case, if we've cut off that resolve later, what the heck? I said resolve. I know it's totally the duck today. Okay, if you have this red one and I cut off that group, what I get is I've exposed this as my new electrophile, which allows me to come in with my next one. This is this R3 in gray. This is my new nucleophile. And it allows me to add that next functional group here to make this next amide bond. So I'm growing in this strategy, I'm growing it from the nitrogen terminal to the C terminal. I couple them together, I expose the C terminal, I make it my new electrophile and bring in a new nucleophile, and it just keeps getting longer. And ideally, you can do this until you build up a long amino acid chain or peptide in this strategy. So the question then is, well, Jason, you just told us that is illegal. You can't take a carboxylic acid and a nitrogen and slam them together. It doesn't happen. Now, you could go in and take that carboxylic acid and turn it into an acid chloride. You could treat this molecule with thionyl chloride. There's a challenge to that, though. Has anybody ever run a reaction with thionyl chloride? Not yet, that's fine. What's the byproduct of the reaction when you do thionyl chloride generally? We talked about this before. If I take thionyl chloride and this, I'm making SO2, that's my gas, and what else? HCl. I don't know if you guys know this. What's in your stomach? Yeah, you take amino acids and you start doing amide coupling like this, where you're generating HCl, you're setting yourself up to do what we call Maillard chemistry, hydrolysis. It destroys peptides. It's not a good idea to just, I was going to use a different word, but let's just go with very brutally do your coupling. This is not something you're going to do with thionyl chloride. Instead, this is where we use what we call carbodiimides. Carbodiimides are your activating groups, which gives us the ability to activate carboxylic acids. They're very active, but they're not as crazy as acid chlorides. They're way more controlled. Now, if you look at these carbodiimides, this molecule, what's the hybridization of that carbon in the middle? sp2, sp3, sp. This is the sp center. What does this kind of look like? There's another functional group, was on the midterm as well, which was NCO. What did we call that? This is like an isocyanide. These are electrophilic right here in the middle, and these are basic or nucleophilic out here. We can protonate those centers, which activates those nitrogens. These are kind of like imines and isocyanates all capped together. So what's nice about these is we can activate the DCC for electrophilic coupling with just a little bit of catalytic acid, And more importantly, the carbon in the middle is super electrophilic. It allows us to couple these pieces together. I can take a carboxylic acid, I can take my carbodiimide, that NCO type system, and I can activate this oxygen. It turns out that, and this is something I mentioned before when we talked about like just amide bonds, this is actually a global problem. Making an amide bond is as simple as I want a nitrogen to attach to a carbonyl and I want to extrude water. 1 oxygen, 2 protons. In order to do this programmatically, I need to blow acid, base, solvent, and all of these atoms just to remove that oxygen. That's really all we're doing here is I'm converting that 1 oxygen into an electrophile, ripping it out of a molecule. This produces what we call very bad atom economy. It produces a huge amount of molecular waste because all I really did is rip an oxygen out of a carboxylic acid and stick it into what we call this. Does everybody remember that functional group? It is right there. It's called a urea. Nitrogen carbonyl with two nitrogens with a carbonyl in between is a urea. So this is what we do. This is actually best in class, is to use these DCC type reagents. Now the way that they work, I'll show you the mechanism here. You start off with your carboxylic acid. You start off with your DCC. Now these are molecules that they are electrophilic in this carbon in the middle, but the way that they really kick off is first we deprotonate. We do 2 things when we do this. Just like what we talked about with like diazomethane. We're using the relative basicity on that nitrogen to pick off a proton that both activates my electrophile, my DCC is being charged up because it's now positively charged, but we're also increasing the nucleophilicity on our carboxylate. What I'm doing is I'm converting this to O-. That's now a much more nucleophilic center, and I now have C+N plus, I'm just going to abbreviate that as R. That's my cyclohexyl group. Man, that duck. I think it actually chases my pointer. I think that's what's going on. So I make a molecule like this that is now charged on this side. So what I'm doing here is I've taken, like an imine, remember reductive amination? In order to do reductive amination under weak acid conditions, I protonate my imine, I turn it into a better electrophile as an iminium. It's kind of like what we're doing here. Now that I've got this, it is now ready for nucleophilic coupling out to here. Now draw this structure. This is a really important structure because if you look at this, you've got your R, your carbonyl, your oxygen, the new bond we just formed. Actually, I'll write that in red. New bond. And then I've got a carbon, double bond. Actually, no, let's draw it that way. N, R, and then down here, N, H, R, where that's your cyclohexyl there and there. What does that look like? Carbon, oxygen, carbon with 2 pi bonds on either side. We had a different functional group we named on this one. This looks like an anhydride, right? This is similar to R, double bond O, O, double bond R prime. So this, what we've done, yes, we didn't get to acid chlorides, but we got to something that's almost as good. This is sort of a nitrogen version of an anhydride buried into this molecule. We've now made that oxygen-carbon bond. That's the piece that we'll be using for a urea. So these are now very, very electrophilic right there. And more importantly, why is it only electrophilic at that green carbonyl? Why is it not electrophilic at that carbon with your 2 nitrogens and oxygens? Remember what this is? Yeah, go for it. Because of resonance again. You've got all of these. Remember, we did the same thing when we're talking about the mixed anhydride method. You've got all these lone pairs around that blue carbon. Those lone pairs help to donate in. It helps to shield or make that not very electrophilic. It's the same thing we used to do when we had a carbonyl, oxygen on the other side. Anhydrides that instead of using a T-butyl group but an OR group also shut down the electrophilicity over there. So we have a single electrophilic site. It means that nucleophilically we can only add here. And the nice thing about that is this is where we bring in our second molecule. This is where we bring in our amino acid. As long as I've got a free amino acid here, I can do a nucleophilic coupling. Now, before that, under these conditions, you could also draw this as, remember, we still have acid-base. We still eventually have to get to something where we have to protonate out or add one more proton to this system. So we have to bring in our nucleophile. We're going to attack this. But this is our standard nucleophile up sort of case, right? That's going to give us our tetrahedral intermediate. This is our standard N-acyl substitution chemistry. So I'm going to draw this, redraw that intermediate on the second page. Actually, no, let me grab this one first. Oh, God, you duck. Ugh. This happens every year. April 1st shows up, and it's like, you guys suck, man. Okay. What's even better is I bet it doesn't screen record, and you all just think I'm crazy. Okay. So if we do this addition, nucleophilic addition of our nitrogen into here is going to give me this zwitterionic intermediate. We're adding a nitrogen into an anhydride, and from this point, that mechanism is identical to the anhydride addition pathway we've done so far. We're going to undergo a proton transfer. That's going to end up sort of move pieces around. Notice that what we have as far as a leaving group over here, we've still got this other center that we have to actually protonate. So what we can do is either, well, we're going to undergo a proton transfer reaction. Let's get it back to just, let's say, the anionic system. So we're going to have our O minus, O, C, double bonded nitrogen, R, and our N, R, H. What else am I missing? After proton transfer, let's keep it red, and H, R prime. So now what we have to do is this goes in, that goes out, right? We can draw this as that fragment. What we've done at this kind of core now is I have made my target amide. The rest of the molecule, we just have to sort of show what happens to it. We've got our carbon, double nitrogen, R, NH, R, and our O minus at this point. We've ejected this as a resonance stabilized fragment. All we have to do to end it off to get to our final component, we're going to bring in this and pick up a proton. That's going to get you to your final urea. Right? What we're doing is we're closing off that last charge, one more protonation in the course of the reaction. So basically what's nice about this is your DCC is effectively acting as a base as well. It picks up one proton for when you're doing your first activation, picks up a final proton when you form urea. So if you look at what you've taken from the system, first proton comes from DCC, second proton picked up by DCC, this final urea, and one oxygen. That's your H2O. The actual condensation reaction, the hydrogens from nitrogen and the oxygen from a carboxylate are all accounted for when we do this reaction to give us our final product here. That's how we've done our water removal. So this is the good copy from your overall mechanism, right? What you're doing is activation of your DCC first. That increases your electrophilicity, adds in, this gives you your final component where you then do your nucleophilic plate. Again, this is similar. Well, all we've done is fuse together our imine, our iminium chemistry, the electrophilic activation of something like our anhydride. So this is how we do our coupling. So the three things I've given you today is a strategy for how we selectively protect nitrogen. Those are our chloroformates and our carbamates. A strategy for selectively protecting the carboxylic acid. Those are your esters, base and acid sensitive. And finally, a selective way to do activation of your carboxylic acid. Those are your three general steps for all the amino acid synthesis I described through here. This coupling is going to be your DCC. You choose your protection, deprotection, and then every coupling is going to be a DCC step that you do in between. And it's just about choosing which fragments, which order that allows you to build up these peptides. It's almost that simple in the end. So this is going to be your practice try it now question. Draw this mechanism. How does this work? And what would happen if you change the acid-base components in this sort of system? With that, you guys made it. This is the final part. Thank you, guys. Seriously, it's been a really, really fun year. I will be available. We'll find some other time that I can help out with different points, and I'll be posting up the sample midterm soon. Have a great week, guys. Okay, so for the problem today, we're asked to draw the product of this following reaction. So the important thing to do here is just look at the two fragments we have, identify which groups are present or which groups are available. And notice the conditions, we're doing 2 steps over here. So step 1, step 2, which is going to go through 2 transformations. So after both of these, we're looking at our final product. Now let's look at the component. This is our electrophile. Okay, this is our exposed carboxylic acid, excuse me, duck. And that makes this my nucleophile. Given that nucleophile, again, that's just because we were exposed nitrogen over here. So that's the coupling we're making. This is the amide that we're going to be attaching into that carboxylic acid. So in step 1, DCC under these conditions is going to activate this carboxylic acid. That's going to give the intermediate we showed you back over here, right? That's effectively this guy right here. So DCC activation of the carboxylic acid will give us that anhydride-like species. Then under those conditions, the nitrogen nucleophile is going to couple. And after step 1, and I'm going to use step 1. After step 1, I'll use the fragments. We use this one as our red fragment. It's going to be our Bach, NH, and this is a methyl group. You can always go back and, if you're interested, look up which amino acids these particular side groups correspond to, but that's alanine. And then we've got our that fragment. The nucleophile, nitrogen, will couple to make our amide, and that gives us this guy. It's our isoleucine, I think. Oh man, I can't remember now. Anyway, and our methyl group over here. So that's the product after step 1. After step 2 now, we're treating it with TFA. That's effectively a deprotection step. It's not just workup. And if you look at this molecule, we have 2 functional groups. We have a carboxylic acid protecting group. This is our ester, and we've got our Bach group over here. If you look at the conditions we have, these this functional group over here is going to be base sensitive at this side. So this is our acid sensitive functional group here. So we're going to do a deprotection of this Bach under that second step. So what that's going to give us is our now free amine on this side, carboxylic acid, and carbonyl, and our nitrogen double bond. Let me move this over just a bit here. So we have our group, our alkyl group, double bond, O-methyl. Now, that's what we would get under these 2. The coupling step and then the acid deprotection step will give us this, where we've cleaved off that Bach group. How would the project change in step 2 was base instead of acid? Let's say we treated this with, let's say, sodium hydroxide. Under sodium hydroxide type conditions, what we're doing is we're going to do base cleavage. We will not touch this one. This group here is hydroxide sensitive. So all that would happen is we would leave the base in place. This would be converted to carboxylic acid after workup. Now, one quick note about the conditions if we're using TFA or this acid. As we mentioned, TFA, usually we do this at low temperature and we use just trifluoroacetic acid. We're just using the acid on its own. And that's going to be selectively doing this deprotection of the Bach group. Since we don't have water present, we don't have to worry about cleavage of things like our amide. The amide will cleave under acidic conditions with heat, time, and water. Usually what we're doing is these acid-sensitive groups, both the T-butyl group, if we had it at this center, if we had a T-butyl ester, or this Bach tertiary butyl group, both of those are much more acid-sensitive and can be done selectively just with a low temperature and just treatment with TFA.